Hello, scholars. My name is Ira McIntosh, and this is Hypothesis. Hey, everyone, and welcome back to Hypothesis. We're back in the office and ready to go with another amazing conversation. This week, I have the immense honor to talk to Dr. Erika Hamden about astrophysics and outer space. And how galaxies are formed, how telescopes work, the fact that there is actually dust in space. It blew my mind. There's dust in space. There are clouds of dust just hanging around in the vacuum of space. And we talk about what that means for the future of space travel as well. This conversation seems really apt at this moment because in the US, there's the possibility of NASA being even further defunded, and people don't seem to understand the implications of space travel and of studying outer space and what that means for understanding our own planet and where we are in our solar system. So join me as I talk to this incredible person about their research and what they do. A little bit about Dr. Hamden before we get started. Dr. Erika Hamden is a tenured professor of astrophysics at Stewart Observatory at the University of Arizona. She has been the director of the UA Space Institute since 2023. She specializes in building space and stratospheric telescopes and developing technology to make telescopes better. Dr. Hamden is a leader in the field of space astrophysics and has created programs to teach early career scientists how to develop their own space missions, NASA's PI Launchpad. She is the PI of Hyperion, a MIDEX mission concept, and the PI of EOS, a SMEX mission concept, to be proposed in 2026. She is the deputy principal investigator of Aspera, a NASA Pioneers smallsat telescope in development for launch in 2026. She is also the institutional PI of Fireball 2, a UV multi-object spectrograph balloon mission. Dr. Hamden received a bachelor's in astronomy and astrophysics from Harvard in 2006. She worked as a chef for a year before beginning grad school at Columbia University. She worked with Professor David Shiminovich, finishing her PhD in 2014. She moved to Caltech for a postdoc, working with Professor Chris Martin, and was an NSF Astronomy and Astrophysics postdoctoral fellow and the R.A. and G.B. Millikan Prize postdoctoral fellow in experimental physics at the California Institute of Technology. Dr. Hamden was awarded a Nancy Grace Roman Technology Fellowship for her detector work in 2016. She received a PCASE award in 2019 and has received numerous other awards from NASA. She is a TED Fellow, an AAAS If Then Ambassador, an aspiring astronaut, and a social media influencer. She recently published a book, Weird Universe. Please enjoy this conversation with Dr. Erika Hamden. I truly was so intimidated this whole time, and she made me feel smart. So I hope that you can come along on this journey with me and feel smart as well. Let's listen. Here we go. Yeah, I also, as I was thinking about what to wear for this episode, I was just like, I want to wear something that feels like Star Trek Next Gen
Yes,
and makes me
absolutely.
feel spacey. So
You look fab.
thank you, as do you. So okay, I don't even know where to start. So I have to admit, that in the articles that you sent me, I went through and skipped over all the math parts because I am terrible at math. And I was like, oh, look, equations, that's fun. But then from what I understood, you study some really, really cool things. Um,
Yes.
and But before we get into those, I was just wondering what led you to your PhD and to being a professor, because you went to some incredible schools.
Yes, I have like a very good pedigree. My parents paid a lot of money. Um, so I've always been really into space. Like since I was a little kid and I learned that space existed, I was like, oh, I like this. And I wanted to go to space, which I still want to do. I've applied to be an astronaut 4 times, but I felt like, okay, I know that not that many people go to space. So the next best thing is to just like think about it all the time and send stuff to space. And I like have I feel like I'm very fortunate in that I've known that this is what I love since for like almost my entire life. Like I'm 42 and I think I figured it out when I was like 6 or 7. Um, and then I was also very fortunate that I was really good at math and science. And so going through grade school, I was just like, oh, this is easy. It was fine. I never really got discouraged. A lot of people are actually good at it, but they get told that they're not, or they like don't have the tools to like become good at it. Um, and I had older sisters, and we all had the same last name. So when I was going through high school, like actually my whole academic career, everyone knew my family. They like knew my sisters, and so they were like, "Oh, the Hamdens are smart." So I think that's why I never got discouraged in anything because everybody knew me and my sisters who are also very smart and have achieved a lot. Um, and then in college, I did have like a little bit of a I went to MIT and dropped out, and then I went back to college. I went to Harvard, and I didn't realize like actually out of those two, Harvard is better at astronomy and astrophysics. MIT is like, of course, the engineering powerhouse, but I got to Harvard and I realized like, oh well, if I want to do space from the science side, this is actually a better place to be, and that was like pretty lucky. um, and but partly like having dropped out of MIT, I had made a decision that I wanted to make sure my like when I was making these big life decisions of like, oh, should I go to grad school? Should I like take this job? Should I move this place? That I was doing it because I really wanted to do it and not because like it's what other people told me I should be doing. Um and that's been really helpful for me that like I feel like when I look back on my career, the like choices are because like I want those things and they're the choice for me. So, being a professor is a great job, but it's also like it's like the culmination of all these other jobs, and like every step of the way people get weeded out. And so my view was like, I just want to do something that's fun and interesting as long as I can keep getting employed to do it. And having the degrees that I have, like I could go work at a bank, I could like do a bunch of other
Mhm.
things that maybe would not be as fun. So, and now I'm tenured, and so I sort of made it and can just like
Yeah,
do what I like.
you could breathe now.
Yeah.
No, I definitely get that. I very quickly when I was younger, I got my undergrad and then went directly into my first master's degree,
hmm
and was did both of them because it was what people told me I was good at and what I should do, and I was like, okay, I guess that's what I'm going to do,
Yeah.
because at least in the US there's this expectation of you finish high school and you go directly to college, and I didn't really know what I wanted to do, so I just did what everyone told me I was good at.
Told you. Yeah.
And then I finished my 6 years of school between undergrad and grad, and was just like, I hate this. I don't want to do this. This was not a waste of time, but it was just like, okay, what do I do now? And then I took 10 years off and just lived life and took time to figure out what I was interested in and what I was good at and what actually made me want to keep studying and made me want to keep going. And
Yeah.
then I went back to school and got another degree, and I'm going from there. But yeah, I think that's a really good and important lesson, is to really be aware of what you're interested in and what you're good at and what's going to keep you going. Because if you want to go into academia, that's the only thing that's going to be rewarding to you.
Yeah. Yeah. And like I think your experience is really interesting because I feel like a lot of people would benefit from like spend some time out doing something in the world and figure out if like an academic life is something that you really want, or if you're just like one of the problems that I feel like professors have is, if we're giving advice to a student, and if the advice is just like, oh, do what I did, then like you want like there are professors who want the student to make the same choices as a way of validating their choices from the past, and like
Yeah.
that's not helpful to the student. And that's like sounds like a lot of the advice that you got that was just like, oh well, I went to grad school, so you should go to grad school. And like, yeah.
Yeah, I find myself very often encouraging people to just not go to school yet. Go to school when you feel like it and when you're ready for it. It's not a necessity right away. For a
Yeah.
lot of careers, you don't need, especially higher ed degrees, you don't need them. So figure out that you need it before you go for it. Because
Yeah,
it's
like for
expensive.
me, for me, I mean, I'm lucky and also in that the STEM like PhD programs are all like paid for. So like I didn't have any debt from 7 years of grad school. Like I was paid, I had a stipend, and like my tuition was paid for by the grant. And um but the like process is so onerous that like you really have to go because that's what you want to do. And like I between college and grad school, I went to cooking school and I worked as a chef for a little while, and that was a good taste of like some something else that I was interested in. But doing it, I felt like, oh, I miss thinking about these like complicated problems. I miss like learning something every day. I miss like being challenged all the time. And that
Yeah.
was a good sign, like kind of what you said of like, oh, I want to go back to academic world.
Yeah, absolutely. So you went to school specifically for astrophysics then, or what degrees got you to what you're studying?
So my degree from Harvard is astronomy and astrophysics, just like a bachelor's. What's amusing, maybe only to me, is that to get a degree in astronomy and astrophysics, you basically have to get a physics degree plus you do a bunch of extra classes. But I didn't feel like filling out the form my senior year to do like a double major. So then my students are like, "Oh, should I double major in this?" And I'm like, "Actually, nobody will care." Like,
Yeah.
um, so all of my degrees are in astronomy and astrophysics. For Columbia, where I went to grad school, it's all astronomy and astrophysics. I knew that like a lot of places will have a physics department and you can do like an astronomy specialty, but I knew that for me, what I really cared about was like the stuff in space. And I didn't want to have to get super bogged down in a bunch of like very nitty gritty physics stuff. Like I didn't want to spend a semester learning condensed matter physics when I'm not ever going to do that. I like wanted to focus on like stars, galaxies, like all the specific things of astronomy. So I only looked at grad schools that were in astronomy departments. Like the U of A, where I am now, has a huge astronomy department and a huge physics department, but they're pretty separate. Whereas a place like Stanford or MIT actually only has a physics department, and there are astronomers there, but they're like a little sub field within a bigger department. So for me, having astronomy as like the primary thing was really important.
Yeah. That's interesting that there isn't as much crossover because I feel like, at least because of pop culture, a lot of people would think, oh, physics, especially theoretical physics, that includes outer space. So astrophysics seems like something that would
Yeah,
always go together.
it does. And what I think is interesting is like most of theoretical physics, not all of it, but a lot of it is motivated by stuff that we find in space. And it's like, how do
Mhm.
you explain this wacky thing? But for the theoretical physicist, I think they view there's definitely some like how do I want to phrase this delicately? Like some theoretical physicists view astronomers as like butterfly collectors, where it's like, oh, you're just looking at a bunch of stuff, but you're not and cataloging it. And they view what they do as like more real. I mean, in some sense, astronomy is applied physics, but like everything is applied physics.
Yeah.
um, so it's more just like philosophical, and also I think it depends strongly on what the student body can support and the what the university is trying to do. So like in a lot of places, there just aren't enough students to have a whole separate major that is astronomy, because if you're adding these extra classes and there's only like 5 people in the class, it's hard to like sustain that. Here we've historically had all these telescopes, like telescopes on all the mountains around Tucson, that we've owned and operated for ages. And so that I think is the reason why our astronomy department is so big, because like the observatory was founded around the same time that the university came into existence. So it's like always been a prevalent part. Whereas like for physics, that came more as just like the normal parts of a university.
Okay, so that actually leads me into one of my first questions, and I'm going to probably ask you some really stupid, very basic questions
No
during
stupid
this.
questions. There are no stupid questions.
Well, so I feel like I should know this answer because back in my undergrad, I went to Hawaii for a month as a study abroad, and we like went to the top of Mauna Loa and visited the telescopes there and visited the research center down um in I don't remember the name of the town, but the actual like where they sit in front of the screens and see what the telescopes are seeing.
Yeah.
But
And I think
I
that's in Waimea, right?
yes, thank you, Waimea. But how I feel stupid asking this question. How do telescopes work? So I know like earthbound telescopes are mirror, a lot of them are mirrors that bounce light around, right?
Yes. Yes. So, so basically, like the way that I think about telescopes is what you care about is like the overall collecting area. So, and this maybe this is like a very convoluted explanation, but okay. So if you're like outside at night and you're standing in your backyard or on the sidewalk or something, and like you look up, you can see the moon, you can see stars from where you're standing. So like the light from those objects is like coming to that location and like hitting your eyeball. If you cross the street and so you're like, 30 feet away and you look up, you can see the moon and the stars. You like see all the same stuff. So the light from those objects is hitting where you were standing on one side of the street and it's hitting where you're standing on the other side of the street. And basically, if you have a telescope, you're taking all of the light that is hitting a certain area and just like gathering it up so that it gets detected at a particular image like point or like a detector or a surface or your eye if you're like looking through an eyepiece. So you're trying to take advantage of the fact that you can use all of these photons that are sort of like raining down everywhere and like get a chunk of them and then collect them all into a single area to then record the image. So the sort of primary mirror like diameter or the aperture tells you how many more photons are you going to get than if you just like use your eye. And then the photon gathering capability is actually just from the behavior of mirrors and using the idea that like light travels in straight lines, it bounces in a very predictable way, so you can create these very customized surfaces to direct the light to a single point where then you put a detector and then you can like collect all the photons, measure how many there are, and then make a digital image or put your photographic plate there, whatever your detector type is. So the actual what's interesting also is that telescopes they use no energy. Like the
Mm,
collection of light is a completely passive process. Like the detection itself is like more active, but you have mirrors and then they just like the light just bounces and ends up where it ends up. You can like reverse them, which is how you get microscopes, but it's like actually like a um an energy neutral kind of entropy neutral process, which I think is very interesting.
that is
Versus
very cool. I
versus
never
like a
thought
lot of
about that.
other scientific instruments, like you need to power them, you need to like be doing a lot of stuff. And for like just your basic telescope that you're looking through with your eye, like requires no energy at all.
Yeah, that's I've never thought about how yeah. That's really cool. Does that apply, do the same kind of physics of that collection apply to telescopes that are sent into outer space as well as telescopes that are on Earth, or does
Yeah.
it function differently?
So they basically function the same. There's some differences. So like if you have an X-ray telescope those have to be above the atmosphere, but X-rays are such energetic photons that if you have like a flat mirror and X-rays are like coming at it, the X-rays will just like go through the mirror. They like don't stop at the mirror the way that a visible wavelength photon will bounce off the mirror in a predictable way. So the X-rays, you actually have to you have these like mirrors that are basically like concentric shells, and the X-ray like grazes along like the side of the mirror, and then so you have to have these very long telescopes because you're just like gently shaping the X-rays into a point. um but it's all like, even in that instance, once your telescope is designed and fabricated and up there, like there's no power involved except again to run the
Mhm.
detector or to like run the communication system of your spacecraft. But they're all passive. They just like sit there and collect. We refer to it as like collecting photons, like you're gathering rain in a bucket or something.
Wait, so that's really interesting. So X-rays, because X-rays are low frequency, they're below visible light, correct?
They are high. They're higher frequency. They're very high energy.
Okay. Interesting.
I'm like, what's the? They have very short wavelengths, and so they're like doing this all the
Got it.
time.
Okay.
Yeah.
No, that's interesting because so my background's all in music, so I'm thinking like sound waves, high frequency sound waves just bounce. They don't go through things. Um, so when you're like in your car sitting next to a car that's playing bass heavy music, you hear the
Yeah,
bass
you can
because
hear
those are
it.
long, slow frequencies that kind of warp their way around things rather than the treble, which is high frequency because that's just bouncing around in the car and can't get out. So
So what's
that's it's
interesting is it is for like light, the wavelength of the light kind of determines it how it interacts with stuff. And so for X-rays, their wavelength is so small that um they like can much more easily pass through things because the
interesting.
interaction size is smaller. So
Okay.
certain like denser materials, they'll like that's what they notice. But if they're just passing through air, or passing through like skin versus your bones, they like don't notice certain things.
That's so cool. So it's almost the reverse of sound. I love that kind of stuff.
Yes.
Um, so okay, so then what does so you've sent a telescope into outer space. What does that collection look like? Like how do you get information from those telescopes that are sent out? Are they like the James Webb telescope that are going like way out into deep space, or are you working with ones in our atmosphere?
So so there's one that I'm working on now that's going to get launched next year that is going to be in low Earth orbit. So it's a higher orbit than the International Space Station, but it's not as far away as like James Webb, which is in a very distant orbit. Um, and it's not even as far away as like geosynchronous satellites, um, which are higher orbit than like normal low Earth orbit. But so basically, the telescope is actually a lot more complicated to operate. Maybe that's not surprising. It's like in space, but because it's it's going around the Earth every 90 minutes. Like the orbits are so fast that the real challenge is like you have to have a series of objects around the sky, basically, so that if this is the Earth and the telescope is here, it's like looking up, and then as it orbits around, at some point it can't like look up anymore because the Earth is in the way. So then you have to be like, okay, now we're going to look like this way, and then it keeps going, and then you have to be like, okay, now we're looking this way, and like so it always has to be looking outward. And so in a single orbit,
Hmm.
which again is only 90 minutes, you're looking at maybe 2 to 3 targets. And so you have to just have like a very precise planning. That's like, okay, we look at this target for 20 minutes, then we slew the telescope to look at this other target for 30 minutes, then we slew to look at this other thing, and then we like stop observing and downlink the data because we're over the ground station in Svalbard or whatever. And then the downlink finishes, and then you point at the first object, and then you like do it over and over and over again. And then on the ground, you get all this data that's like in pieces of the same target, but you need to like do the analysis and then be able to kind of stitch them together so that they're seamless. So it ends up being um, really like a whole thing. Like there's a huge amount of like computer programming and like image analysis and statistics to like figure out like how do you reconstruct the image of the galaxy based on these
Mhm.
like little piecemeal observations.
So then is it usually like a single researcher that's using uh the same satellite just looking at multiple objects as it orbits, or is it multiple researchers that each choose one object that are all using the same satellite to research with?
So it depends on the telescope. So like for like JWST or Hubble, there's like a whole process that's repeated every year where people put proposals in. They request a certain amount of time to look at a certain target. Those proposals get approved or like selected or not selected by a time allocation committee that like evaluates the science benefit and then kind of ranks them. And then they see like, okay, how do we fit all of these together over the course of a year? Like certain targets, JWC, for example, cannot look towards the sun, the earth, or the moon. It has to keep its like sun shield always pointed towards the sun. So there's certain targets, like if you want to look at an object in Orion, but Orion is towards the sun, you have to wait 6 months until we're on the other side of the sun to then look that way. So there's a lot of this like scheduling that goes into it. And then um, people are assigned a certain amount of time, but then it can get split up. Like Hubble is in a low Earth orbit, so if your target is there and someone else's target is here, as Hubble is going around the Earth, like it'll switch between your target and someone else's target, and then your target and someone else's target, and until all of your time has been used, or until the Earth has moved enough that those targets are no longer accessible. So it's a whole. There's like a whole sets of people that just do the like all the scheduling. It's actually extremely like complicated, and especially for those telescopes, like every second really matters. Like you want to maximize the usage of it, and so the people that do it, they it's actually like I think kind of stressful job because also sometimes
Yeah.
there'll be what's called a target of opportunity where like if a supernova goes off somewhere or like in the instance in 2017 there was two neutron stars that merged that was detected by LIGO, the gravitational wave interferometers, and the when that happened basically every telescope on earth and in space like dropped whatever it was doing to like
Yeah.
look for the merger and the supernova. So if you're like one of the Hubble schedulers, like you have to be able to um, fit those things in on top of this already very complicated um, schedule. So a lot of telescopes operate like that. Some telescopes, when they're first launched, they have like kind of an observing program that's already set aside. So they'll do that, and then they'll start asking people for submissions for other investigations.
Got it. So are those schedulers who is where are those schedules like located? Are they part of NASA? Is there like a
They're usually
centralized hub of scheduling?
so so they're normally like they work at a non-NASA institution, but their budget comes from NASA. So for like
Got it.
Hubble and JWST, the schedulers are at this institute in Baltimore that's called the Space Telescope Institute, because they were originally set up for Hubble, and so they were called like the Space Telescope Institute for Hubble, the Space Telescope. So they do Hubble, JWST, they'll do future big telescopes, and then other NASA telescopes, like the institution that kind of PI'd the mission or that runs the telescope, will do all of those kind of mission operations. So for the most part, they're kind of like spread around at different institutions. There's like a center at Harvard, there's the Space Telescope folks, there's a couple at Caltech, um, or like for Mars rovers, for example, like JPL drives all of the Mars rovers from their like mission control in Pasadena. So yeah, I guess it's spread out, and a lot of people that do it, like they have PhDs in astronomy or physics or planetary science, or sometimes they're engineers, and they just ended
Mm,
up um, working on some part of the mission, and then as the mission extends, they're like, oh well, I want to keep being involved in it, so they spend part of their time doing these kind of logistical things that just keep it running, and then the
mhm.
other part of their time they're doing research that they're interested in.
I mean, it sounds like
in a nightmarish way, it sounds like a fun puzzle to deal
Yes, that's a really good descriptor of it.
with. Okay, so focusing in on kind of your area of research, I let's start with a very base question again. I noticed words like cloud and gas and dust and things like that coming up in the articles that you sent me. What are the differences between those things? Like how do you decide what is outer space gas versus dust versus a
Yeah,
cloud?
so the gas is basically like uh any like single atoms that are just floating around. So like an atom of hydrogen, an atom of oxygen, an atom of like nitrogen, um those are just like gas particles. And the dust is something that's much more like complex and basically dust is like conglomerations of like carbon atoms for the most part. It's like similar to actually if you like take a pencil and like it's like the graphite. And there's a bunch of other junk mixed in there, but it's basically these will be these like little conglomerations of particles, but it would best be characterized as like a solid. They tend to be really cold. You need to have a lot of heavier elements. Most of the universe is just hydrogen and helium, and that's it. And so you need there to be like stars that have been born and then died to create all this other stuff to get the carbon to make dust. So dust is kind of an indicator of like what in astronomy we refer to as metallicity, like how much non-hydrogen stuff is there. Whereas you can have gas that's just hydrogen and that's fine, but the dust requires like all these heavier elements. Um, and then clouds are usually a combination of gas and dust, but at higher densities. So, um, out in the interstellar space just beyond our solar system, there's like a few particles per square meter. It's very diffuse. There's like not a lot there. Whereas if you go to like the Orion Nebula where new stars are forming, you'll have hundreds of particles per square centimeter, like thousands of particles per square meter. There's just much more stuff in any one volume.
Mm,
So we usually define clouds as above a certain density where you have a combination of gas and dust and a certain kind of um, over density that indicates like, oh, maybe stars will form here, maybe something is happening. So the cloud is like the the object, the dust and the gas are what like make the object.
that is crazy to me. And I feel like it shouldn't be crazy to me because conceptually I understand that there are things in space, obviously. And I feel like I'm failing Ms. Frizzle in her rudimentary astronomy
Oh,
lessons that she gave me on Magic School Bus. But the I feel like I'm just actually like piecing it together now that there's physical things. Like when you say dust, it's literal
it's like
dust.
actual dust. Like,
I think in my mind there was just like this. It felt like, oh, it's just this like light structure out in space. I don't know why it didn't make sense to me that it's literal dust.
yeah, it's like I mean, it's wacky and it's funny too because like dust is like there are people who just like spend their whole career studying dust and like how much is there, what type of it is, because there's different um like depending on the size of the grain of dust, it has different behavior, different optical properties, like it's made of different things. And like is interstellar dust the same as intergalactic dust, the same as dust like coming off a star or whatever? Like it's so wacky that
Yeah.
like you can like dive deep into anything. But yeah, it's ultimately just like the same shit as here.
Well, it makes me now consider. I don't know why my light suddenly got so bright there. There we go. Oh, okay.
It's
Well, you know what? It is what it is. I'm now under
like a
stage
filter is
lights.
on you. Yeah.
Yeah, yeah, it's great. It's because the sun is setting, so whatever. I love it. Um, but it makes me reconsider while I'm watching things like Star Wars and Star Trek and thinking about going faster than the speed of light, if you're hitting like actual physical objects and dust going that
Oh yeah.
speed, you're going to be destroying
Like
your ship because you're going
yes.
that fast. There's no, it doesn't make any sense to me now.
Yeah, like
I think you just
the
ruined space movies for
oh
me.
no, space travel is
No, I'm kidding.
impossible because your ship will get eroded away. But actually, like I do you think that it's underrated how harsh the conditions are putting things in space? Like when they put the Hubble Space Telescope up and they revisited a few times for these servicing missions, and like it is not looking pristine up there. Like things get like pitted and they get hit, and like that, you know, low Earth orbit is a little bit dirtier than like being out in interstellar space, but yeah, you like I mean, maybe Star Wars is acceptable because they like jump to hyperspace, so you're technically not traveling just like super fast. But yeah, you are gonna run into a bunch of things, and there'll be friction, and like it'll peel the paint of your
Hmm.
spacecraft, and it's tough.
How dare they make a movie and not take real physics into account? How dare
I
they?
know.
So one of the things that struck me, and I may have just misunderstood, but in one of the articles you sent, you were talking about the local bubble being
Oh
our
yeah.
closest star nursery, and that our solar system is part of that. Does that mean
Yes.
that our solar system is still technically forming? Is it still very young cosmically, or is it like an older
We
sibling?
we just like have wandered. I actually just made an Instagram video about the local bubble that I think I'm gonna post tomorrow, but we just wandered into the local bubble. Like so
Okay.
the local bubble probably formed 10 to 20 million years ago when a supernova went off and like basically cleared out a bunch of the interstellar space, and just like all the energy from the supernova acts like a shock wave that like pushes everything away. And the sun formed like 4.5 billion years ago at some other part of the galaxy, and it's been like it orbits the center of the galaxy every, I think it's like a couple 100 million years is the orbit. We've done like 20 orbits in our the sun has done 20 orbits around the galaxy since it formed. So
Wow.
it's in college, in galactic years. But
It can
the
almost
sun,
drink.
yes, exactly. This is so close to being able to drink. Um, the sun just wandered into the local bubble like 5 million years ago. And
Okay.
so we're like in it, but then we'll eventually leave and be in a different part of the galaxy. But
Okay.
you know, our entire existence on Earth as humans, and certainly all of our astronomical observations have happened while we're in the middle of this local bubble. So it's really it's the part of the galaxy that we have the best view of because we're in it.
Mm. So that means that we have a good view of how these structures form because we are so close to them, quote unquote, close to them
Yeah.
currently.
Yeah, and like if we were instead in like you know, much closer to like a place where there was a ton of star formation happening, our view would be really different and maybe worse. But because we're in this like cleared out area, it's actually kind of nice because it gives us a really good view like out of the galaxy. Like the supernova that caused the bubble like kind of creates like a window outward because all the material got cleared out. So we have these nice views like out looking, you know, out of the galactic plane. Our view through the galaxy is still harder because there's so much stuff there. But it's kind of cool that we're in this little bubble for right now, and it's interesting to think like how much less would we know about like external galaxies if we were in a
Mm.
super dense part of the Milky Way where it was really hard to see out. Like we might think that external galaxies were rare just because our view is really bad.
Is that why when you look up at the night sky in a less populated area, you can see the Milky Way because we're in a less dense part of it?
Uh,
Did I just misunderstand what you said completely?
well, so it's actually like you can see you would be able to see the Milky Way, um, wherever we were in it, but it's actually the inverse. Like we can see the Andromeda galaxy, we can see other galaxies because we're in this less dense
Mm,
part of our galaxy. Like our galaxy
got
doesn't
it.
take the entire view everywhere.
Got it. So it's like the difference between being in the middle of a city and being out in the
Yeah.
world, being able to actually
Yeah.
see
Like
things.
we're in the boondocks of our galaxy where, and like actually it's like there was recently an explosion that leveled all the trees. And so now we can like see everything because we just happened to decide this was the best place to build our house.
Perfect. Perfect. Um, so okay, so I wrote a lot of questions that I probably don't understand how to phrase correctly,
Okay.
but but
I
in
love
reading
these
that
questions are so
article,
good and they're like so fun and so spacey. So I
well,
love
thank
it.
you. Thank you. No, I like to pretend I'm smart because I watched Magic School Bus growing up and I visited a telescope once.
I mean, that's
Um
all it takes.
Truly, I mean, absolutely. All you need is a 90s cartoon and you're set. Um
Yes.
so in the article that you sent me, um you were using far ultraviolet fluorescence to
Yes.
track hydrogen. Um, and you also said that it's hasn't really been done as much recently because dihydrogen is a lot harder to track than carbon monoxide.
Yeah.
Why is
Yes.
that? Because you just said that space is mostly like most of the particles are
Hydrogen.
hydrogen and helium.
Yeah.
So why is it harder to track the hydrogen than it is the carbon monoxide?
Yes. So that's a fabulous question. So in the clouds that we kind of talked about, like you have an overdensity of hydrogen. If like single atoms of hydrogen become cool enough, or if there's enough dust, they will bond together to become hydrogen molecules, which is two hydrogen atoms, dihydrogen, um, bonded together. That's the most abundant molecule in the universe because it takes the most abundant element and you just need two of them and then it sticks together. And um, molecular hydrogen helps to like actually shield the rest of the cloud. Like molecular hydrogen absorbs some of the energy that is coming from like the rest of space that could maybe destroy the molecules of the cloud and like basically
Mm,
the cloud can get eroded away from just like external energy sources or a star or whatever. So the molecular hydrogen helps to kind of shield the interior of the cloud. Given enough time, the cloud will condense, like gravity will pull things together. The cloud will also cool off. And so you'll have these denser, colder regions in the center of the cloud. And that's where carbon monoxide forms. So carbon monoxide will form, um, and there are these other molecules, more complex molecules that will form if the cloud is cold enough and dense enough. When we observe the galaxy, carbon monoxide has a transition in the near, I think it's the near infrared. It's pretty easy to observe. So carbon monoxide that's like just lightly warm will glow a little bit. And so that's something that we've mapped the entire galaxy, the plane of the galaxy in carbon monoxide. And so we can say like, okay,
wow.
well, carbon monoxide only forms under these conditions. So here's where all the molecular clouds are, but you're not really looking at the full cloud. You're just looking at the core of it, like the very coldest,
Mm,
densest parts. But there's this like envelope around it, which is just molecular hydrogen. Molecular hydrogen only emits in the far ultraviolet. It fluoresces where basically like the two molecules will like like the two atoms are vibrating in the molecule, or sometimes they like go like this or like this or like doing a little dance with each other. And this action like emits photons, but they're far ultraviolet photons. And historically, the far ultraviolet was a very difficult wavelength range to work in. And so we don't have that many telescopes that do observations at that wavelength range. People were like, well, we can see where most stuff is by just looking at CO, so that's good enough. But what we showed with this paper and what we're trying to prove with a couple of proposals that we have is that actually like the CO is not good enough and you're missing these huge regions, either clouds that are completely self-contained but don't have any CO in them, or you're just missing like these huge chunks of the cloud that aren't super dense for a variety of reasons. And so if you look only in the CO, you're really missing it. So the CO is like 1,000 times less abundant than the molecular hydrogen. And so our group, we want to build a telescope that will just look for all that molecular hydrogen and actually do like a real map and a survey of it. And And it's funny because, you know, stars are made of hydrogen. Where stars are forming, there is always a lot of molecular hydrogen, but we don't know, like, do you have to have molecular hydrogen? Could you make stars out of just straight hydrogen? Like, do
Mm.
they just happen to be in the same place, or is it actually like a causal relationship? And so one of the things that we want to explore with this telescope concept would be to like do these molecular hydrogen observations and really get a better sense of like how much is there, how is it behaving, is it like what's the temperature, what's the density, um, how old is the molecule, like when did the molecule form, and like and to try to link that to the star formation that's happening within the cloud. So like it's a kind of funny, our current view of like these star forming regions is as if we could take an X-ray of the cloud and see deep within, we could see like the bones of the cloud, but you had no
Mm.
idea like what the skin looks like or like anything on the surface. So
So we're
we like
seeing
really,
like star fossils, but not
yeah,
actual creatures.
yeah, exactly. And like we want, let's see the whole creature.
That's fascinating. Wait, so how does that, just trying to put it into things that I can visualize a little more easily. So when we see like images of these space clouds and these star nurseries that are sent out to the general public from NASA, are those then just images that are created from those CO2 or the CO
See,
maps, or are they
um,
including other molecular structures?
sometimes they have others. So frequently it'll be a combination of CO, oxygen, molecules or oxygen atoms. Sometimes there'll be nitrogen. Sometimes there'll be atomic hydrogen. So not molecular hydrogen, but just like atomic hydrogen. But most of the like JWST images, for example, you're looking at CO and you're also looking at dust. Like the dust is very visible
Mhm.
in the
Okay.
JWST images. So and actually JWST can pick up a tiny amount of molecular hydrogen. But for the most part, those images are like a composite of dust, CO, a couple other elements.
So really those pictures are like a fraction of what's actually there because they're not able to catch those hydrogen atoms interacting with the cloud.
Yeah, and they're looking like it's a little deceptive because you look at the image and it looks like you're looking at a surface, but you're actually looking
Mhm.
like deep within. At it is a surface there, but it's like not the surface of the cloud. It's like a structure that's very far into the cloud.
That is something that I've
It's
noticed. I remember there was like a movie that was at the science museums. Um, we used to go to the Oregon Museum of Science and Industry, the OMSI, a lot as a kid,
mm,
and they had a film there at one point that must have been late 90s, early 2000s, where they were like, we're going to go into these clouds, and they like figured out a way to do 3D images out of the 2D images that were recreated, but it was clearly like some kind of CG that
yeah,
approximation.
yeah,
um but it really makes me curious as to how, because I feel like space to a lot of people, at least to me, is a very kind of flat thing in our minds because we're just used to seeing
yeah. The
pictures. We're not used
images,
to seeing
yeah,
the depth. And in your articles you were talking about parsecs, and I know it's a distance. I know I'm enough
yes.
of a Star Wars fan to know that it's
It's
not a length of time, but
not a length of time.
I'd never looked up how far it is, like what the distance is. And just really quickly for listeners, a parsec is 3.26 light years, which is roughly 30.9 trillion kilometers or 19.2 trillion miles. And
Yeah.
you were talking distances of like 100 to 350 parsecs, and
Yes.
I can't comprehend that depth of space. It's insane.
And
I
that's just like right around, that's like the neighborhood. Like,
Yeah, like I theoretically, sure, I know space is big, but when you start talking about it in those terms, it's really terrifying.
Yes,
And really explains just the depth of field that we're talking about.
yeah, like I have a book that came out just a couple weeks ago that's like sitting right over there. That one of the chapters I talk about is like space is really big, and it feels like such a non-statement to be like, yeah, space is big, and everyone's like, yeah, space is big, and I have to be like, no, you don't get it.
Yeah.
Like, and and that's partly why people are always asking me about aliens, because they like have no conception of just like how
Yeah.
big space actually is. That like, oh, it's really big. Like you could, like Voyager, the thing that is farthest from us that we've sent, is going to be traveling for like 30,000 years before it even gets to the next star. Like it's like it is like these not like completely inhumane numbers and distances and
Yeah.
time scales, and like people just cannot get their brains around it.
Well, and I remember as a kid when the first Mars rover was sent out, and they were like, "We sent it. Now come back in 15 years and it'll land
Yeah.
and we can talk about it." We were like, "Wait, what?"
I'm like I'm working on this. I'm like helping one of the faculty members here with a potential instrument for a mission that NASA is considering, 5 to 10 years in the future, that would go to Uranus,
Oh,
which isn't
wow.
even the farthest planet in our solar system. Like it's closer than Neptune, and like the launch dates in like the 30s, and then the time that it takes just to get there, it's like 15 years. Like we're all going to be retired by his time that it's like there. It just to see like, and that's like that, like Uranus is in the neighborhood, and it
Hmm.
just takes forever.
So in that case, as a researcher, do you then set up questions and experiments and research questions that then can be passed easily to the next researcher? Like, how do you create research when you're not even going to be the one that gets to answer the questions
See
that
the
you're
data.
asking?
Yeah. So like it's interesting because we have to, like, we talk a lot about like succession planning, where it's almost like,
Mm,
and like it's not for when you die, it's just for when you retire, or when, maybe you take a different job and somebody else, like you might get promoted and like be running a department or whatever. Like lots of things can happen, but you need to have a plan in place for like, okay, well, if it takes 15 years to get there, then the pipeline to analyze the data, the like planned list of observations, like you have to, store all of that knowledge and make sure that it gets passed down to the people that are going to actually be doing it. So it's funny to think of like it's a little bit of thinking of your own mortality, like as
mm.
you're like, someone else will carry on the work. You're like planting a garden for, that you're never going to see, but somebody else will be in the garden.
But also, it's kind of beautiful in a way as a researcher to know that the questions that you're asking are still going to be relevant and important in the
Yes.
next couple of decades, because people are going to be required to look at the data that you're collecting.
Yeah.
So
And like
there
one
must be
thing,
some kind of joy you get from the fact that you're not going to be forgotten because your experiment is still
yes.
going.
And like I tell people like, the research, all research is important because you don't know what's going to matter.
Mm,
And
mhm.
like you can't know ahead of time. I mean, I think that knowing how a star forms is valuable just to know it, just to like understand the universe and the world around us. But the example that I use is like Einstein developed his theory of general relativity, of like the nature of space time, how it changes, how masses move in it, because he wanted to explain how the world worked, because he saw these strange things and he wanted to be able to say like, why does the speed of light behave in this way? Why is the orbit of Mercury the way that it is? And that was it. That's the motivation. He just wants to know. He wants to explain. But now, in over 100 years later, like general relativity is the reason that GPS works. If we had put up
Mm.
GPS satellites and we didn't understand general relativity, like everything would be wrong all the time, and every day would get worse. Like the time between the distance and timing between satellites, like you requires general relativity because the satellites are moving so quickly. And that's the kind of thing that I point to, that's like, you don't fund, research into the fundamental nature of space-time because you're expecting to make money from it in 100 years. But like, but maybe you can. I mean, I don't think the point of anything is to make money, but the basic idea is like, nobody now knows what's going to matter. Even 10 years from now, like what little bit of research is going to unlock something. So
Yeah.
for me, that provides the motivation to be like, well, you got to flood the zone and just like figure out everything.
That's
And
why
it's a
if you have what you
fundamental
think
human
is this,
desire.
yeah, and that's why if you think you have a stupid question, look for an answer, because it might not be a stupid question.
Yeah, it might actually be like, I mean, some of the things that people are like, oh, I have a stupid question for you, and then they're like, what is gravity? And I'm like, that is like the deepest, most complicated question that you could ask me.
That actually is a beautiful segue into kind of the last big question that I have for you is, I gravity is something that people are constantly talking about, and there have been multiple Nobel Prizes over the last couple of decades with people offering new theories about how it works. Things like entropic gravity and space-time defects, and the how dark matter and dark energy affect things. But my question around that is less about those actual things and more about, I know that a lot of those theories are considered controversial. So what is the use in a controversial theory? Like, why is something that is considered controversial winning a Nobel Prize? Like, how does that spur on new research?
So what's interesting is, so like science in general is very like small c conservative. Like scientists need to see a lot of evidence before they're going to buy your theory. There needs to be like a bunch of different experiments, a bunch of different tests, a bunch of different ways of like modeling something. And like the so on the one hand, like scientists like are like, oh, I don't believe you, you have to like show me all this information. But at the same time, you need people who are willing to like push things a little bit forward to like try and like be like, okay, I don't like this part of this theory, I want to like see if this is right, and they like go off in a side direction. And sometimes those side directions are not actually side directions, it is the direction. And even like general
Mm.
relativity, when Einstein published it, people did not like it. He never won a Nobel Prize for it. He won Nobel Prizes for other work that he did, but for GR, like, no. Even though it is the like thus far is like our best explanation of gravity. Um, but so you need people who are willing to be like, okay, I'm gonna like explore this wacky thing and see what happens. Like, um, there's a lot of examples of that with like people, like people thought that black holes were just like this mathematical um, curiosity. It was like a mathematical outcome of general relativity, but they were like, there's no way that this is real. Like this is too, they didn't even really think about what its implications would be. And then people started finding these strange objects in space, like very dense neutron stars, and then eventually black holes. And then so the observers, this is a little bit of how like the astronomy can sometimes drive the physics, because like people were finding these strange objects, and then you need to go back to the model to be like, okay, how do you explain this? Or like, is this already in here? We just thought it wasn't real. Um, so there, in order to make progress, like there have to be people that are willing to like go out on a limb and like try something and be like, hey, I have this crazy idea. Like, what if dark energy is changing over time? And like, then you have your hypothesis and you test it and you see if it's right or wrong. And like, so the process requires people to both be very cautious in accepting new concepts, but at the same time encourage people to go try new things, because that's the only way that the whole like field moves forward. But there's always these people that are out at the vanguard, like at the front, and everyone else is in a big clump, like slowly following them.
Yeah, I mean, even in the areas that I study, both in music but also in sociology and anthropology, in those areas, you need people who are creative and willing to think outside of the box, or even ask weird questions and say, okay, but what if this thing that we've been talking about for 100 years is completely wrong? What if
Yeah.
Einstein was an idiot and it's actually the exact opposite of what Einstein said? If that was the case, how would these things work in order to move things forward? Because if you're not questioning what came before you, then everything is just gonna stay the same and you're never gonna learn anything new.
Yeah. Yeah, and like the process, if it's going well, should be self-corrective. Like you could be like, what if Einstein was wrong? Here's my experiment, here's my hypothesis, like here's the data. And then other people can like do the same thing or like do a variant of it, and like, and then so I always view it as like science is never looking for the truth. It's like you're like just always like slowly circling the actual like nature of reality. But you know, as you get closer you realize like how far away you are, but you're still always like kind
Mm-hmm.
of getting close to it. And I think that's actually something that people who don't do it like don't like about research overall, is that like it's iterative, and like you're wrong and then you're less wrong and then you're maybe right and then you're less wrong, and like you're never there's never an answer that's like, no, this is it.
Yeah. Even in math, even 1 + 1 does not always equal 2.
Yeah, depends on your definition of one.
All
Although
right. Well, let's.
when I started when I started college, I enrolled in like a more advanced. There was like applied math for physics people, and then there was like a more advanced math for like math people. And I like went to like two meetings of the class, and like they like proved that numbers existed. That was like the first step. Was like proving that numbers were existed at all. And I was like, oh, this is not the math for me. I need to like know how to do like differential equation. Like so I like went back to the math for physics people.
Oh yeah, yeah. Math never. Nope. There was never a math for me. I could not find one that made actual sense. Well, that brings us to just a few minutes from the end, and so I like to ask for audience questions. And I got a couple from someone, and they're both very deep
Okay.
questions. So we will see if we have time for both, but we'll start with one.
Okay.
So audience question time. At Touche Likes Beef on Instagram asks, the multiverse is everywhere in the media these days. What portrayal of the many worlds theory is the most authentic to the core concept that you have seen or learned of, and why?
Um, honestly, probably the version that's in Everything Everywhere All at Once.
Mm,
Um, where there's like an infinite number of, yeah, that, or actually like there was an Apple TV show last year called Dark Matter that was great.
okay.
And in both of those pieces of media, the most of the universes or the worlds that they go to are like dead and bad and
Mm,
lifeless and like um and so I actually think that it's I'm like ultimately an optimist, so I feel like, okay, I think the universe is infinite. In an infinite universe there are an infinite number of other earths that are just like this earth. Like there's an infinite number of earths that are different, like the dinosaurs didn't get wiped out and everyone is like a T-Rex. But like there's an infinite number of earths like ours that, but only slightly different. And that's kind of what those two shows are about, or the movie and the show. And yeah, and I also think that like I like their portrayal in that, in my perspective, if there are multiverses, it only makes sense for there to be like our single limited experience or an infinite number of them. I think it's very hard to justify like why are there
mm,
only 10 universes or 10 other versions, or like even two feels hard. Maybe there's like a mirror, but anything other than one, two, or infinity, I feel like you can't, doesn't make sense to me. Um, so I like that in those two portrayals, there's like the number of possibilities is like uncountable.
like that. I guess the second question is just kind of a fun question, so I'll ask that one too. They also asked if you had to postulate a viable faster than light method of travel, hyperdrive, warp drive, wormholes, etc. Since we talked about this earlier, I figured it was relevant.
Oh
What would
yeah.
that look like and how could it be achieved?
So I think that I like the idea of a faster than light travel that involves like opening up of space time in some way. So like we know that space
Mhm.
time can be warped by like mass. We know that it can be like what like is there a word for when you like drop a rock in a pond? Like it can be
Like
like
a
rung
ripple
like a
effect.
bell. Yeah, like you can
Okay.
ripple space time. Um and so I think that for me what I envision is like some way to like almost just like cut a seam in space time and like
Mm,
go into the like it could maybe it's another dimension, maybe it's just like the like the underlying matrix of the universe or something, but like I think that actually I think is the only way to achieve faster than light travel is to be able to manipulate space-time in such a way as to like get through it
mm.
instead of
So it's
existing on
almost more
it.
like time travel than it is what we would think of as like space travel from movies and TV
Yeah,
shows.
like you'd be like exiting the universe and then coming back somewhere else almost.
That sounds terrifying. Like you
Yes,
are
like don't,
just ceasing to exist
yeah,
momentarily.
don't worry about it. You'll be back. You hope you'll be
Well,
back.
okay, well, moving on from that terrifying nightmare of an answer, I have what I like to call my synthesis questions, which are questions that I ask everyone, and these are just rapid fire. So just
Okay.
what comes to mind when I ask them. So the first one is, what is your typical like executive dysfunction or rest day activity? Like when you're so
Right.
stressed, you just got to do something else.
So I usually like cook a bunch of things. I'll do
Mm,
like a big like cooking project. Um maybe do some yoga or like go for a hike. And then eat my big cooking project.
nice. What is your favorite setting for working on your research?
I actually love to be in my office. I like I'm not a work from home person. I like to come in and have like my list of things to do. I like write it down, and then if I'm like really on it, I number the list and it's like, okay, first I'm gonna do this, like 1 2 5 1 2 3 4, and then I do it in order. That's like actually my best work day, which weirdly doesn't always happen, even though I could just do that every day, but sometimes
Mhm. I get it.
it's just not gonna
As a Virgo,
happen.
I get it. What is one thing that an advisor has told you that has stuck with you? And this can be positive or negative.
um oh my god, so many things. I've had such great advisors, but so my thesis advisor, he so I was a graduate student. He was he always would have all these undergraduates working for him, and it was like their first research experience. And I remember I was finishing my grad time, and so I was going to go, become a postdoc and then start mentoring people. And he was like, it's important to remember that when you're mentoring people, like sometimes it will take them 100, maybe 1,000 times as long as it would take you to do it, but that's
Mm,
not the point. And like I think about that a lot because I've had to like work very hard to overcome the feeling of like this would be faster if I just do it, because like the point is for them to learn and then eventually they can do it as fast as me, but like I have to give them that space.
it's really good advice. And I feel like I should let myself use that advice for myself.
Yes. And like,
um,
oh, go ahead.
if you could choose any other area of research, what would you choose?
Ooh, um, so I actually like, oh gosh, I think nuclear physics is super cool. So probably I would do that, but that's still like applied physics. But I also think that viruses are extremely interesting
Ooh.
and weird and like a little bit alien. Like they have no desires, no agencies, but they wreak havoc. It's just so weird. So I I find that cool.
Who is one other academic whose research you really admire?
Um, oh, that's tough. There's a lot of people. Like, there's a few other astronomers. There's this woman at ASU, Arizona State, which is in Tempe, like in Phoenix, and is always confused for the University of Arizona. So we're like, there's two different Arizonas. So this woman, Eugenia Skolnick, who's a professor there, and I like really admire her work. Like we overlap in certain realms, and I got the opportunity to put a proposal in with her last year, and working with her was just like really nice. Like she's so clear and but also like careful, and I felt like her she like exemplified to me like the scientist who like wants to just follow the evidence, and but at the same time she was like really human and caring. And so yeah, I like, maybe I'll say her because it was a new experience to work with her. We like hadn't worked together, and I was just like, oh my gosh, you're amazing. And that proposal ended up not getting selected, so like we're not working together now, but it was a great experience to be like, oh, maybe we could team up again.
Nice. What is one question that you've never been able to answer?
I mean, what is gravity?
If only we could answer that. If
Oh,
only.
I then you would be introducing me as Nobel Prize winning Professor Erika
Yeah, exactly.
Hamden.
And then last question. I know a lot of us in research fields are required to present our research in Times New Roman, but what font do you wish you could present your research in?
um, I I like I'm like I have no idea. I use LaTeX. It's this like old-timey typesetting software from before there was Microsoft Word, and it is like there's a web interface now, and you can it's like much easier to use, but it just has this like standard, it is a serif font, I think, but I just like write everything in LaTeX. And so actually I get mad if someone makes me use Microsoft Word, because I'm like, I don't care about any of these things. Microsoft Word, you like move something by like one line and the whole document blows up.
Ooh,
Um,
yeah.
so yeah, my maybe this is my like extremely scientist answer, but I'm like, I just want to use this typesetting software developed in the 1970s. Like,
I
don't make me
love
do
that.
anything else.
I love that. Well, thank you very much for your time. I know you are so busy, but thank you. This has been really an honor to be able to talk to you about this.
It has been so fun to talk to you. So thank you for having me on. It's been just a delight.
And we will talk to you all later. Bye.
Bye.
What a truly incredible conversation that was. I really have no words for what just happened. I was mind blown the entire time, and I hope the questions that I asked were questions that you would have asked, and questions that helped you understand astrophysics and outer space a little bit better. So just a huge, huge thank you to Dr. Erika Hamden for coming on the podcast and being a guest, especially so early on, taking a chance on the podcast with me. I am so very grateful. If you would like to submit a listener question to the podcast to be asked of future guests, please feel free. You can add us on Instagram at HypothesisPod and send us a DM there. You could also email us at hypothesispodcast@gmail.com, or you can go to speakpipe.com/hypothesispodcast and send in an audio question as well. Again, that's speakpipe.com/hypothesispodcast to submit an audio question, so you can hear your own voice on the podcast. That's pretty cool. Be sure to follow us on all of our socials. Again, our Instagram is at HypothesisPod. You can also follow my Instagram at Ira A. McIntosh, or TikTok at The Gay Ethnographer. Please, please, please subscribe and rate and review and do all of those things on all of your favorite podcast listening services. And please share this podcast. The only way for us to get information out there and to broaden people's horizons and get people excited about education again is if you help us and share this podcast. It can only go up from here, and we are so excited to see the response that's coming in already, and we're ready to see what happens next. So please, let's fight misinformation together. Have a wonderful day and go read a book.